Hey everyone, long time no see. I hope you're staying warm. Figured I'd go ahead and record this. Just I don't know. I'm snowed out. I've got nothing better to do. So today we're talking about a introduction to data structures and algorithms. So start off. I remember last class I asked, "What is a data structure?" Got some really good answers, and the simplest way we can put it is a data structure is a way to organize data so that it can be used effectively. One thing you'll learn about me is I use a lot of similes and metaphors while I'm teaching just to try to take it and apply it somewhere else in our lives. One way you can think about data structures is interacting with people. If I go into the next faculty meeting, throwing all this Gen Z slang, uh, my fellow coworkers and colleagues probably aren't going to know what I'm talking about. If I walk up to a Dr. Eberly and start talking about Riz, he's probably going to be confused. So what we can do is we can take this data that I want to talk about, to my colleagues about, and we can shape it and reform it to be coherent. So that same thing applies with data for programming and all these other different aspects. Is maybe the way it is now isn't the best way to present it, and we have to change it to get it to fit. Next thing to ask is why should we care about data structures? These are absolutely essential depending on the data you have and the problems you want to solve with this data. Through my graduate degree, I did data science and AI. And so, I may gripe and I may grumble about this class, but a lot of the things that you learn in this class is applicable in data science. Now, that's not to say that you're never going to use this if you do cyber or high powered computing, because HPC also needs queues and stuff. But, you know, there's more to life than grim and gloom. So, first thing we're going to talk about are arrays. So, an array is a linear data structure that contains an ordered list of items. We've all worked with them, we've all seen them, hopefully at least. And they're great for just storing generic elements. They can be one dimensional, two dimensional, three dimensional. If you're feeling super spicy, you can go into the higher dimensions. That's not for me though. And so each number that we have can be put into one of these boxes. So let's say I'm taking age of classmates, who knows? So let's put like 18. Do I have a pen? Let's do that. So, someone's 18, someone's a boomer, like 25. And so we can store numbers in these boxes. One thing to keep in mind is with this, we have to look at use cases with these data structures. Like, yes, we can put numbers in boxes. That's crazy, but why would that matter? What's the use of that? So one thing I would like to, talk about is pixel art. Don't worry, this will make sense. So if we come here to this beautiful looking cat, he's orange, so you know he's a bastard. We can see individual pixels with the art. And if we put on our computer science hats, we can see that this is just a 2D array. So if we go this very first pixel right here, this is going to be, 0, 0. It's a brown pixel. If we go the next one, 0, 1, another brown pixel. Brown, brown, brown. I guess it's more of like a deep brown. Brown, we have some red pixels right here. If we go like halfway through, I'm assuming this is like what? 30, 30, let's say 30, 30. We have a green pixel. And so if we take that same logic of two-dimensional arrays and look at our own monitors. So I have all of these pixels that need filled, and we can think of it as just one big thing of pixel art. It may be missing some of the nostalgia aspects of pixel art, but it's pixel art nonetheless. And so, boom, we're already using arrays. Check that off the list. So, next in the data structures are lists. So, lists are standalone, but they're also kind of building blocks of data structures. So lists are linear data structures. So we form a sequence, a line of data, if you will. Each box is called a node, and each node contains data and at least one link. So with linked lists, you can have singly linked lists, doubly linked lists. There's a couple others that are super cool, but we won't touch on because there's no need to. And the best way to visualize and think about linked lists, or at least doubly linked lists, is Spotify, Apple Music. Let's say you're sitting there, you're just going through songs, can't find one you like, and you accidentally skip a really good one. Well, if it was implemented using a singly linked list, we couldn't go back. But since doubly linked lists point both ways, I should have probably put that first. So the difference between singly linked lists and doubly linked lists is doubly linked lists connect both ways, forwards and backwards. Singly linked lists only connect forwards. So in this diagram down here, the node 10 connects to 15, 15 connects to 77, 77 connects to null. If it was a doubly linked list, 15 would point to both 10 and 77 would point to both 15 and null. So back to the metaphor, I'm so sorry. So I guess it wouldn't be a metaphor. With Spotify, it has to be implemented using a doubly linked list, meaning that each song connects forward and backwards, meaning we can skip forward to a different song or we can go back to a previous song. And the idea of lists and linked lists and nodes and pointers and stuff like that is applied to the different data structures we'll cover. We have to cover stacks, queues, heaps, lists, but you'll see a whole lot of at least the nodes, pointers sort of aspect of lists. So next data structure is a tree. Another linear data structure. Often, I don't know how to explain it. So as you can see, there are a whole bunch of different trees we can have. We can have binary trees, binary search trees, B trees, heaps, trees, AVL trees, red-black trees, and more. In the example we have below, we have just a simple binary tree. Within a binary tree, each node can have 0, 1, or 2 children. If we start working our way down the tree, the very top node, 7, has 2 children. Its left child is 18, and its right child is 91. Its left child, 18, also has 2 children, and its children have 2 children. So let's take a look at the right child of 7. So 91 has 1 child. Its one child is 10, and its other link outside of the node points to a null spot. So this null spot doesn't have anything. It's not considered a child. It's a placeholder in case we want to put something there. If we keep working our way down this list, so 91 connects to 10. 10 has a child, 1 child, which is 28. 28 has no children. It is a completely blank, is a leaf node. So leaf nodes in this case have no children because it's the end, the edge of the tree. So in this tree we have 1, 94, 8, 3, and 28 all being leaf nodes. So there's trees for you. A real world example, a lot of machine learning is based around trees. We have random tree algorithms. We have decision trees. If I have 2 things that I can choose to do, either I go to like Wendy's for dinner or I go cook. Well, the dinner node has 2 children because I have to pick one of them. So next is hash tables. Hash tables are probably, I don't want to say the least common data structure you'll see. I'm sure they're out there somewhere. But it takes the data that you want to store. It does some magic to it. You have to build the magic, unfortunately. And then we take the magic that we have hashed and we store it. A good example for this is the tech usernames that we have. It depends on a couple of different things, but, let's say I am the only B. Vandergriff who works at Tennessee Tech. My email is B. Vandergriff. If another one came along, so let's say that top one, 0, that's my spot, B. Vandergriff. Assuming another B. Vandergriff came along, I'm already in that spot, and so he has to go to the next one. So has to do something to the name, either add a number, maybe use a different letter of their name. But regardless, they took my name, they did some hashing on it, some funny functions, and I got my username out of it. So also applies to student names. Surprisingly, even though only 12,000 people at Tech, there's a couple overlaps. And so, the default number for the student emails is 42. If you see someone with a 43 or a 44, I know some of the last names like Smith, White, Johnson, there's a couple of you. And so once these start to overlap, we have to augment, where we put the name. Usually 42, 43, 44. And that's how we get the usernames for our Tech emails. So next data structure is graphs. So a graph is a data structure that represents connections among items. A vertex is the node of our graph, and the edge connects the vertices. So graphs are super cool. You either love them or you hate them. I haven't met someone who hates them yet, so good news. And they just excel at displaying maybe positional, relational data. I know Dr. Eberle does a lot of research in graphs for machine learning, and even outside of research and stuff, graphs are still fantastic. Because how do you plot data of roads that go out of a town, or maybe people? Who are you friends with? Who are those people friends with? And so these are fantastic examples for graphs. Breaking down graphs a little more, there are two different types. We'll talk about them later, so you don't have to worry about them now. But two different types of graphs. There are undirected and directed graphs. And so undirected graphs are exactly what we have on example. So our A, not quite what I wanted, but A connects to B, A connects to D, A connects to C, and all of these connect back to A because it's an undirected graph. If we wanted to make it a directed graph, we have to start adding that is not thick enough. Hold on. Gotta get my bifocals on, old man. So in this example, let's just start throwing some arrows on here. So let's make A connect. I'm gonna lose it. Let's make A connect to B. D connect to A. Just gonna copy paste this one. So I want A and C to connect to each other. So we're gonna make these arrows point at each other. And so now it's a directed graph, and this completely changes things. So we can go from A to B, but we can't go back from B to A. We can go B to D to A, but we can't go A to D. And then we can go back and forth from A and C as much as we want. One way to think of this is like traveling. If you're trying to book a flight somewhere and you have to make different detours and different stops along the way, maybe if you want to fly from Nashville down to Charlotte up to Pennsylvania, who knows? But we have to keep in mind that maybe our return trip won't look the same. So there's your real-world comparison of the day. Now that brings us to the question of which data structure do I use? If it was a simple, great answer, we wouldn't have this class. So it truly depends on the type of data and the problem that you are trying to solve. What operations need to be done to the data. So, an actual example for once. Let's say we want to add a number to our list. The number y goes in between x1 and x2, and we want to choose the one that's going to take the least amount of steps. So if we go with an array, so we have x1, 2, 3, 4, 5, 6. Well, if we want y in the second spot, we have to move all of this down 1. So that's 1 move, 2 move, 3 moves, 4 moves, 5 moves, and finally an insert. So this one has 6 different steps we have to go through. And that's just adding one number. If we have to do it again, it's going to be 7 steps or 8 steps, depending on where we put it. Could also be less, compared to a linked list, where if we're trying to put it at the same spot between x1 and x2, we're going to take our x1 pointer, because it's pointing to x2 right now, we're going to make it point to y, and then we're going to make y point to x2. So already it's fast. It's a lot more efficient than just working with arrays. And if we have to repeat this hundreds upon hundreds of times, these extra steps will add up and slow us down. So some of the major distinctions between, good programmers, bad programmers, and just fantastic programmers is that the ones who know how to use data structures are fantastic. I could go out and I could apply to, any of the Silicon Valley companies, Meta, I guess it's called X, not Twitter, Twitch, any of these giant companies, and they will take one look at my resume, maybe call me in for an interview, and I will lose to a programmer who knows their data structures, who does their, LEET codes and understands all the small interworkings of these data structures, because they're going to be the better programmer. They're going to have a more efficient result than I will have. So, food for thought, learn your data structures. Moving on to, the second portion of the class title, algorithms. An algorithm is a clear sequence of steps to solve a problem. I kind of jumboed those words, my bad. But, if we have a problem and we want to solve it, we have to plan out how we're going to solve it. Algorithms can be done in a couple of different styles. They can be written in plain English. They can have a flowchart, pseudocode, or they can just be flat out written in a programming language. So, next couple of slides will have these algorithms, the exact same algorithm, in a few different ways. So, if we want to say it in English, we're going to put sum and counter to 0, get n from the user, do some math and put it in sum, and we're going to increment count. If count is less than 5, we repeat it, otherwise we output sum. So, first things first, we can notice that this one is very wordy and very wide. So, it may work for someone who doesn't program that often. These are the type of instructions you get from, a parent or something, like, okay, go to the grocery store on aisle 3, halfway down, the breadcrumbs that I need are on the left. Okay, I guess. So, moving to a flowchart algorithm, this one's super easy to read and follow along with. So we set sum and count equal to 0, we get n from the user, we do some math, increment count, and then if count is less than 5, we repeat. If it's not, we output sum. And so visually, this is fantastic. The one issue is whenever you start throwing in different shapes. So this diamond is a conditional. If whoever's reading this does not know about the conditionals, that could cause an issue. So moving on to pseudocode. We take all of the wordy instructions that we just went through, and we just simplify it. We code it without coding it. And so as you can see, we set sum equal to 0, count is equal to 0, and then while count is less than 5, we loop. So this is one of the simpler versions of pseudocode. You'll see a lot of this within your homeworks and different tests of just raw pseudocode. And it applies to essentially any language, because we're not restricting it to, Python, C++, any of those. You can take this and you can implement it anywhere. And then the most familiar type of pseudocode that you all are probably familiar with, language is hard apparently, is just putting it into an actual programming language. And so good old C++ hasn't failed us yet. So we have a sum variable, a count variable, and n, which are all integers. While count is less than 5, we're going to grab n from the user, do some math, and increment count. After this loop is done, we're going to output sum, and boom, we have an answer. So, why do we need algorithms? Algorithms are such an important aspect of our lives, it kind of hurts my brain to think about. So, algorithms. Whenever we go to Google, let's just do a live example, I guess. And I say, what am I typing? Let's say we have examples of linked list and programming. These are autofill algorithms based on what other people have said, or based off of my history and what the next one is going to be. We have examples of lists, pixel art, which I just looked up pixel art, so it makes sense, digital art, metaphors, personification, figurative language. And so your search engine uses these algorithms to figure out, how do I best help the person find what they're looking for? We have organ donor matching and relationship matching. Anyone on Tinder and Bumble and OkCupid and Farmer's Meet, those are all algorithms being used. If you use GPS, how do we know that this is the shortest path to get where we're going to? I can make it to Nashville if I head all the way north around the Arctic Circle and loop the Earth. Is it the most effective? Probably not. Would it be fun? Of course. Maximum flow of data or water, any sort of recommendation algorithm. So your TikTok For You page, that's all an algorithm. Mathematical calculations. If we know exactly how to do something and we have the instructions for it, that's an algorithm. And so these algorithms can be applied to effectively anywhere in our lives. So looking at algorithm efficiency, a couple different ways to think about how effective an algorithm is. There is time efficiency and space efficiency. So going down the time efficiency route, if you ever want to be a good manager, going back to the business major thing, if you want to move in the higher up circle, I want to be a manager so I can be a CEO, so I can be whatever, you need to figure out how to save money. Money in this case may be the time that people spend on a project. How do you make these projects faster? How do you make their work faster so they can do more and you can make more money? The more time you spend sitting there twiddling your thumbs, well, that's losing money because someone has to pay for that. Second thought is space efficiency. How many of these problems in my life that I could fix with 500 of my best friends to, I don't know, just maul any problem? I'm taking a test, I got my best 500 people on it. But then that comes an issue of, where do I put 500 people working on a problem? That's not a small amount of people. And so, kind of wrangling it back into computer science, think about the last, I don't want to sound like a boomer saying this, but like the last good code we had, whenever we went to the moon. We went to the moon on literally like megabytes of memory, code, and just horrible equipment. And nowadays, we have, you know, 100 times that on our phone and 100 times that processing power on our phone, but it's less effective. And so we may have fixed one problem, but we are suffering in another. Uh, so, food for thought, write better code. And then there are problems that exist where, you know, they're called NP for no polynomial. If you can figure out a polynomial solution to these problems, you can teach this class. You can have my job. It's yours. You're smarter. But these problems essentially mean that there is no way to solve it in a reasonable amount of time, a humane amount of time. Like, yes, we could solve the problem given, 100,000 years. I don't think I can stay alive long enough to find the results. So, one of these is the knapsack problem, or the knapsack algorithm. We have a big backpack, and we are trying to pack it full worth of the most valuable things. Why, we could verify, whether or not our solution is a good one in polynomial terms. Open the bag, look in it. Did that work? No. But if we want to sit there and spin and continuously test, that's going to take absolutely forever. So there's some food for thought, different algorithms. Now we can scoot on down to data types. So hopefully everyone knows what data types are. It's the type of data that you are working with and the operations that you can do on this data. And so things like primitive data types, int, floats, strings, characters, all have their operations that you can work with. You can add numbers, you can move string characters around, things like that. And we also have abstract data types. These are the lists, stacks, queues, maps, classes, structures that we've kind of touched on over the past, 6 months. And so, where do we get this abstract from? Well, abstraction, in simple terms, I'm abstracting abstraction, is you're just taking everything that the user doesn't need to know about and simplifying it for them. The only things that I need to know about my car is like how to change the oil, and when I press on the gas, it goes. Everything else, it's magic to me. I do not need to know. Whereas someone like a mechanic or an engineer, they should probably know how a car works, especially if they are actively working on them. And so if we take all of this data, dumb it down to be simple for my brain, that's abstraction. Another, key idea of abstraction I want to bring up is video games. So I'm sure everyone has heard of, seen, maybe thought of, been told about Undertale. So over the holiday, I found the decompiled Undertale source code. So we go to Undertale source code. It's a GitHub. Undertale has fantastic reviews. Whatever. I haven't played it, but I can respect it. Every bit of dialogue in this game is a switch case that just checks different things. So, spoilers, if you haven't played the game yet, that's kind of your own fault. But if we scroll down here, and if room is equal to 6, the shadow of the runes looms above, filling you with determination. So, does the player need to know that every piece of conversation is a switch case? Probably not. But they don't care because it's been simplified and it's just dialogue. And so abstraction is, how do we make this topic fun for people? How do we make it usable? So if we combine the data types we just talked about and abstraction, is we make abstract data types. So abstract data type is we take the data structure that we work with and we only provide an interface to work with. Going back to the Undertale example, if my only options to move dialogue is forward or back, I'm not going to break it. That's pretty simple to me. So the interface does not give any specific details about how something should be implemented or in what programming language. All I know is that, I can press forward to skip dialogue, and maybe if I skip something I wanted to see, I can go back. So going through abstract data types examples, it's a table that explains the difference between an abstraction of something and its more specific implementation. If we take a list, we can get a dynamic array or a linked list out of it. If we have a queue, we can go for a linked list-based queue, an array-based queue, or a stack-based queue. If we look at a map, we can do a tree map, a hash table. And let's say we took a vehicle class or a vehicle struct. We can implement a golf cart, a bicycle, a smart car, maybe one of those lifted trucks that I hear outside all the time. As long as we give them the tools to do it with, the user can do whatever they want. Finally, we have some abstract data types in standard programming languages. This is just to see, what's out there, what you can use that is readily available. In Python, using the Python standard library, you can use lists, sets, dictionaries, dequeues. In C++, using the standard template library, we have vectors, lists, dequeues, queues, stacks, sets, and maps. And if you are a poor soul who has to use Java, we have collections, sets, lists, maps, queues, and dequeues. So that is everything. I have no clue when you all are watching this, because I'm probably doing the exact same thing in class, so hope you're staying warm. Take it easy, kiddos.